The European Space Agency's mission to search for life on Mars has reached an important milestone with its six-wheeled surface rover prototype ready for its shake and bake. Built by Airbus Defence and Space just north of London in Stevenage, Britain's unlikely space city, the so-called structural thermal model is being packed off to Toulouse, France, for a raft of tests to ensure the real ExoMars rover handles anything the red planet can throw at it. If the 2020 mission goes to plan, it would be Europe's first rover on Mars, following several successful NASA landings. Europe's last attempt to land a rover vehicle on the surface of Mars ended in disappointment in 2016 when Schiaparelli span out of control and slammed into the red sand. The ESA rover will be more sophisticated, though, featuring a 2-meter exploration drill and an autonomous navigation system. That's the most exciting thing that hasn't been done before. We've got a huge 2-meter drill so it can go into the crust, which is where we think life would be if it was still surviving. ExoMars delivery manager Abby Huddy told Reuters. At the surface, the radiation is extreme and conditions too hostile. Down below, different layers of rock, maybe in a fissure where there may be water deposits, could be a nice place for life to still be surviving. Huddy will keep a close eye on the prototype tests in Toulouse, where the launch from a Russian rocket will be simulated, as well as the massive temperature variations it will endure 54 million kilometers away on Mars. Data sent back from the ESA's Mars Express satellite are helping scientists choose the most suitable landing site. The ExoMars rover's autonomous navigation, which will enable it to steer itself rather than wait 24 minutes for instructions from Earth, has been undergoing testing at Airbus's Mars Yard. The Stevenage Center has a mock-up of the planet's surface, complete with specially dried sand, boulders, and Mars-like light intensity, if not the radiation. The main goal of ExoMars is to find out if life has ever existed on Mars. It will do this through a series of instruments on the surface and in orbit. This includes an orbiting spacecraft called the Trace Gas Orbiter, TGO, that carries a probe to study trace gases such as methane around the planet. Scientists believe methane, a chemical that on Earth is strongly tied to life, could help identify areas where life does or could have once existed. The second part of the ExoMars mission, delayed to 2022/2023 due to coronavirus, will deliver a rover to Mars' surface. The rover is being built in Stevenage, UK, and is named after British scientist Rosalind Franklin. It will be the first with the ability to both move across the planet's surface and drill into the ground to collect and analyze samples. The rover will include a technology called the Mars Organic Molecule Analyzer, MOMA, that will allow it to analyze samples and send data back to Earth. Its 6 wafer wheels made of thin strips of metal and unique suspension system means it can scale rocks and roll across the sandy landscape. The cool thing about the wheels is that they are fully metallic and give us the traction and grip of a rubber wheel without taking anything organic from Earth. They will be able to climb over rocks and also dig through deep sand, Huddy said. Once testing is completed in France, work will begin on building the finished rover as well as a twin that will stay in Stevenage. NASA has spotted mysterious spiderwebs on a never-before-explored region near the equator of Mars. The agency's Curiosity rover has been dispatched to probe these bizarre structures, which cover a 6 to 12-mile stretch of Martian desert. As the machine searches for signs that this long, desolate world once supported alien life, geologists suspect that the spiderwebs are a gigantic version of a type of crystallized minerals known as a boxwork, which appear inside some caves on Earth. They can be found on the ceiling of Wind Cave in South Dakota, which were created by calcium carbonate mineral water seeping into cracks between softer rocks that hardened into crystals. But the sprawling, over 3,800-acre-wide boxwork on Mars differs in that it was likely formed by Martian seawater and may have trapped fossils of ancient life in its web. These ridges will include minerals that crystallized underground, where it would have been warmer, according to Rice University geologist Dr. Kirsten Seebach. Early Earth microbes could have survived in a similar environment, Dr. Seebach explained. Nothing that the salty liquid water that created these Martian webs an ideal location to find lingering fossil evidence of ancient alien microbes. The discovery comes as Australian researchers have found that a Martian meteorite, which crashed into northwest Africa, provides more evidence of hot water on Mars. A chemical analysis of that meteorite suggests conditions were ripe for aquatic life to develop on Earth's nearest neighbor over 4 billion years ago. Ever since it first parachuted down to the Martian surface on August 6, 2012, Curiosity has been exploring the red planet for signs of life, as well as hunting for clues about Mars' climate, geology, and where all its ancient water went. But NASA researchers have been intrigued by the massive geological spiderweb for even longer, ever since their Mars Reconnaissance Orbiter satellite first captured aerial images of this haunting landscape back on December 10, 2006. How such formations could appear on Mars' surface is still a mystery, but theories point to the climate chaos that stripped Mars of its water billions of years ago. The likelihood that evidence of aquatic microbial life of Mars might be caught in this giant web as fossils makes this an exciting place to explore. This web of potential dead alien microbes and bugs rests in the shadow of a 3-mile-tall mountain, officially known as Aeolus Mons, but nicknamed Mount Sharp. Past explorations by the Curiosity rover have revealed many sedimentary layers along the cliff faces of Mount Sharp, suggesting in rich detail that it had been formed by water erosion via ancient lake deposits. NASA scientists suspect that this erosion helped form the giant crystal spiderweb, as mineral-rich pulses of water seeped and cascaded down Mount Sharp into fractures in the surface rock and then crystallized. According to satellite mapping work that Dr. Seebach published in 2014, at least 113.6 billion gallons of salty, warm, mineral-laden water would have been required to create the vast field of crystal webbing, which is bigger than Los Angeles Airport, LAX. In Australia this month, scientists working with Martian meteor NWA 7034, discovered after it crashed into northwest Africa, have found still further evidence that ancient warm oceans on Mars could have easily supported alien life. We use nanoscale geochemistry to detect elemental evidence of hot water on Mars 4.45 billion years ago, planetary scientist Dr. Aaron Cavosi said in a statement. Geochemical markers of water were discovered on meteor NWA 7034, Dr. Cavosi explained, based both on the shape of its rocky grain patterns and its chemical composition, telltale signs of water-rich fluids from when the grain formed. A special technique used to date the age of incredibly old zircon minerals via trace amounts of radioactive material called uranium lead dating found that this meteor was made up of some of the oldest Martian volcanic rock ever obtained. The team identified element patterns in this unique zircon, including iron, aluminum, yttrium, and sodium, Dr. Cavosi said, through nanoscale imaging and spectroscopy. NASA's Mars orbiter snaps a stunning photo of frosty sand dunes in the northern plains of the red planet. These elements were added as the zircon formed 4.45 billion years ago, suggesting water was present during early Martian magmatic activity. This mixture of hot and mineral-rich water, not unlike the hydrothermal vents that support life deep in Earth's oceans, point towards the possibility that life was developing on Mars billions of years ago, amid all this volcanic activity. Hydrothermal systems were essential for the development of life on Earth, Dr. Cavosi explained, and our findings suggest Mars also had water, a key ingredient for habitable environments during the earliest history of crust formation. The Australian planetary scientist and his team at Curtin University in Australia published their results in the journal Science Advances this past Friday. In its decade-plus on the red planet, NASA's Curiosity rover has trekked roughly 20 miles of the Martian surface for clues about the life that may have once thrived there. Curiosity will begin studying the spiderweb ridges up close in 2025, according to NASA Administrator Bill Nelson, where it will stay for a month-long journey through Mars boxwork. Scientists have made a discovery about Mars that could lead to uncovering alien life. They identified an 1,800-mile-wide plain in the northern hemisphere that has the right subsurface conditions to support living organisms. The region, called Acidalia planitia, contains just the right levels of water, heat, and energy in its soil for alien bacteria to thrive. The next step is to drill into the Martian surface to see if life truly has sprung there. It is a promising target area for future missions in the search for extant life in Mars' subsurface. The researchers, led Andrea Buttarini of the University of Barcelona, wrote, "But researchers would have to dig miles below the red planet. This would require major crewed missions and technologies that are not likely to be achievable for years to come. This study, however, brings scientists one step closer to finding definitive proof of life beyond Earth by zeroing in on a location where microbial life could exist. What's more, it lays the groundwork for future studies that could settle an intense debate about the presence of methane in the red planet's atmosphere. That's because the alien life forms that the researchers believe could live beneath Acidalia planitia are methanogens, or methane-producing bacteria. Methanogens are extremophils, bacteria that thrive in extreme environmental conditions, such as very high temperatures, ultra-salty water, or even high levels of radiation. On Earth, methanogens typically dwell in swamps and marshes, but can also be found in the guts of cows, termites, and other herbivores, as well as in dead and decaying organic matter. These microorganisms are anaerobic, which means they do not need oxygen to survive. They can also survive without organic nutrients or sunlight. In 2028, the European Space Agency, ESA, plans to launch their Rosalind Franklin rover, previously known as the ExoMars rover. This will include a drill that can dig roughly 7 feet into the Martian surface. But that's not nearly deep enough to access the potentially habitable depth Buttarini and his colleagues identified. The Martian surface is inhospitable due to extremely cold temperatures and low pressure that not even extremophiles could survive. But below the surface, the radioactive decay of elements such as thorium, a radioactive metal, produces heat and chemical energy. What's more, water left behind from ancient oceans is buried within the red planet. These conditions could provide the ingredients for bacterial life, but likely up to 5 miles below. Buttarini, a biogeochemist at the University of Barcelona, and his colleagues used data from Mars orbiters to locate regions where abundant thorium could provide life-sustaining energy. They then matched this data with the distribution of subsurface ice previously mapped by missions, such as the Chinese Zhurong rover. This analysis revealed that the most robust target area is the southern Acidalia planitia at mid-latitude, located near a region of clay and carbonate deposits with signs of groundwater activity. At this underground location, temperatures are higher than they are on the surface, averaging between 32 to 50 degrees Fahrenheit. That means liquid water could be mixed into the Martian soil, and where there is liquid water, bacterial life can grow. But the research is already gaining attention from the scientific community, as it provides a specific location on which to focus the search for extraterrestrial life. In this region, the radiogenic heat-producing elements are at the highest abundance, and subsurface water is likely. If the researchers' theory eventually proves correct, it would not only lead to the groundbreaking discovery of alien life on Mars, but it would also provide indirect evidence for the presence of biologically generated methane in the Martian atmosphere. Observations of methane in the Martian atmosphere have been reported since 1999, but they have always been conflicting. These measurements show highly variable methane concentrations, with global averages ranging from 5 to 33 parts per billion volume. While Curiosity has detected methane in the Martian atmosphere, the ExoMars orbiter has not. This has sparked a heated debate within the scientific community. Finding methanogens living below the surface of Mars would be strong evidence to suggest that the red planet's atmosphere does, in fact, contain methane at least partly generated by microbial processes. Alternatively, atmospheric methane could stem from non-biological processes such as volcanic or hydrothermal activity. Or it could not exist at all. Though this debate is still far from settled, identifying locations where microbial life could exist on Mars brings scientists closer to understanding the true composition of the red planet's atmosphere and finding alien life.